Welcome, everyone. Thank you for joining us today for this session of our HACC Tech Talk series. My name is Mario Ruiz, and I'm today's host. I am part of the AMD University program, and for those of you that are not familiar with this program, uh, the, the Heterogeneous Accelerated Compute Cluster is a special initiative from AMD to support novel research in adaptive compute acceleration for high-performance computing and AI applications. HACC centers have been set up at 6 partner universities around the world. Each HACC site has a compute node that integrates AMD EPYC processors, AMD Instinct GPUs, accelerators, and Alveo accelerator cards, as well as Alversal adaptive SoCs. Members of the programs can use these resources to carry out their own research. The HACC Tech Talks are intended to highlight the applications and research related to HACCs. If you are interested in the program or any of the previous Tech Talks, you can find more information on how to apply in the link displayed here in the slide. So in today's sessions, we have two 30-minute talks. The first one is gonna start with RoCE Balboa, an RDMA deep packet inspection and line rate with ML models on FPGAs. We have two speakers for this presentation. Both Maximilian Heer and Benjamin Ramhorst are second-year PhD students in the system groups at ETH Zurich, under the supervision of Professor Gustavo Alonso. While Maximilian's research is centered around the use of FPGAs and NICs for high-performance networks and in heterogeneous compute systems, Benjamin is mostly interested in reconfigurable network-centered accelerators for machine learning systems. They collaborate on multiple infrastructure-related FPGA projects. One of such examples is the presentation today, RoCE Balboa. And I'm also pleased to say that this work was one of the winners of the AMD Open Hardware competition this year.
So yeah, thanks a lot for the nice introduction. As said before, we are Max and Benjamin from the ETH Systems to ETH Zurich Systems Group, and we'd like to present you our work on RDMA deep packet inspection and line rate with FPGAs. Just to give you a little bit of an idea what's going to happen. Yeah, in the beginning, we'd like to introduce the usage of FPGAs in the cloud. To accomplish that, we need to introduce the networking protocols that are important in the cloud, in our case, especially RDMA and RoCE. Then we'd like to come to the main idea of this project, the deep packet inspection for RDMA on FPGAs, and how we implemented it. First, as integration into our existing networking architecture, and then how specifically the machine learning model behind our deep packet inspection design was implemented and designed. In the end, we'd like to introduce you to our evaluation and networking performance data that we could gather on the HACC, as well as we'd like to give you a little bit of a conclusion and what we think might be important for the future. Just a short hint about this project, as already introduced, it won the AMD Open Hardware competition, and it is right now under submission to ACM FPGA. So just for you to know, there might be some more coming out about that in the future. FPGAs in the cloud. We're all aware that due to the end of Dennard scaling and the end of the validity of Moore's law, more or less, we see a drastic shift in the hardware fleet in data centers for cloud computing. Instead of single CPUs or multi-core CPUs, we are seeing a growing heterogeneity of different accelerators for different type of applications, such as GPUs, TPUs, and most importantly in our context, FPGAs. FPGAs are especially well suited for streamlined computation, and this is why you find them mostly in network-facing or network-attached roles in the data center. We can generally classify two different roles of usage of the FPGA in the cloud. First of all, acceleration for user-defined services, for example, the AWS F1 architectures in the Amazon cloud that allow you to deploy all kinds of acceleration, for example, for RTL simulation. And on the other hand, you find FPGAs used as reconfigurable NICs in the data center. So basically as networking cards that allow you to do networking on the one hand, and on the other hand, to offload certain networking functionalities. This is what our research currently is about most of the time, and which is also the key thing that we try to explore with our project, RoCE Balboa, how to offload certain functionalities such as DPI onto a reconfigurable NIC. To understand a bit more, we now need to dive deeper into the networking protocols that play a huge role in the data center. And this is nowadays mostly RDMA, or more specifically RDMA over Converged Ethernet, so-called RoCE. RDMA is nothing else but remote direct memory access. You might know direct memory access from the embedded context. RDMA just adds the networking component. The idea is that you have two different applications running on two different remote servers, and now you want to communicate data between these two different applications. With RDMA, they can exchange data directly via the NIC. On the one hand, the NIC pulls data from the buffer associated with one application, sends them over the network, it is received on the other side in the NIC, and directly sent to the buffer of this other application via DMA. As you can see quite clearly in this graphic, the operating system is bypassed all the time, which saves you a lot of overhead. So one of the performance factors that this idea is based on is obviously host bypassing. The other one is zero copy, because you don't need to copy data from user space to kernel space. And lastly, you can use polling to get a quick termination of every transaction that you have. This leads to performance benefits, most importantly, high throughput, low latency, but also low CPU utilization, which is quite important for the business model of the cloud. And finally, the ability to perform asynchronous operations. For your better understanding, it is quite important to know that RDMA was originally developed for high-performance computing over the so-called InfiniBand fabric, and then later adopted for the public cloud for data centers, for which it was transformed as a protocol over Ethernet. This is why we now mostly speak about RoCE, RDMA over Converged Ethernet, more specifically in the version 2. The graphic down here shows you that on a typical day, you have around 70% of all networking traffic in a typical cloud, in this case, the Microsoft Azure cloud, being RDMA traffic. So without any doubt, without any question, RDMA has become one of the most important networking stacks, networking protocols that you have in the public cloud and data center computing. However, not everything is great about RDMA. Coming from high-performance computing with its vastly different security and trust assumptions, there are some security weaknesses associated with RDMA. Most importantly, host bypassing, which ensures its great performance, also means that we're bypassing all security mechanisms that are possibly implemented in the operating system. Secondly, adding up to that, the RDMA stack lacks all of the encryption and cryptographic authentication that you would like to have in a modern networking protocol. And lastly, the existing RDMA security features, such as the R keys or the memory protection areas, are quite weak, and there are multiple papers out there, for example, the work by Konstantin Taranov here from ETH, that show how easy it is to attack RDMA systems, spoof connections, hijack connections, and send stuff that shouldn't go there. We have a quite drastic image here. You see an existing RDMA flow, which is used to exchange images for machine learning, for example. And then there is a connection hijacker taking over this established connection so that the remote host, the remote receiver, cannot detect anything is going on wrongly. But now the connection hijacker is sending malcode, malware, or established connection directly into memory of the receiving system, where it can directly start to access stuff and gain control over the receiving system. The question is now, how can we solve this problem? Well, on the one hand, we have a certain urgency because there are big gaps in the security of RDMA. And on the other hand, some of the facts, some of the circumstances to establish this urgency are also performance relevant, for example, the host bypassing. This mixture of urgency and performance criticality leads to the fact that we have to offload the security and access control onto the smart NIC, where the data is already flowing through, where you can make very quick decisions at line rate to find out if a connection was hijacked, if the stuff that I'm receiving is malicious or should be acceptable. This leads us to the little bit more broad question of networking access control for RDMA. The idea behind networking access control is that the user can define rules about what content is allowed to enter from the network, and more specifically, how to proceed with certain networking contents that are received over the network. We have come up with two different use cases where this might be relevant. First of all, a very obvious use case is the defense against shellcode. Shellcode is malicious code, malware as you might call it, that is hidden in the payload of otherwise normal looking packets. And if it is accepted and written into the memory, it can cause great damage, take over control of the system. Our networking stack, our FPGA NIC, tries to detect such shellcode in packets and block them. That would be our networking rule, our networking access rule implemented here. Another, a little bit less drastic example for networking access control would be content area routing. So we have a smart NIC which can detect which kind of files are transported in networking payload and can then route them to different applications on the receiving host, for example, to databases or machine learning based on the content that we are just receiving. How can you implement such kind of networking access control to solve the problems of RDMA? Well, our solution to the problem is packet inspection, deep packet inspection. The idea behind packet inspection in general is that you extract information from incoming networking traffic and make a routing decision based on this gathered information. In this case, mostly, should we forward the packet and write it to memory, or should we drop this packet, ACC or NACC? We have standard packet inspection, which uses information coming from the headers of packets. The advantage of header-based packet inspection is that the information is already structured and it's quite easy to do those checks at line rate. On the other hand, however, the information in headers is not very expressive when it comes to sophisticated attacks. So it's very easy to spoof a header to make a header look as expected, right? The more interesting stuff is going on in the payload, and for that we need deep packet inspection. The payload is expressive, and it is very important for all kinds of advanced attack schemes because that is where I would send a malware. But at the same time, since it is very much unstructured information, it is hard to analyze payload in real time. It is hard to do line rate deep packet inspection. Our idea is to use machine learning deployed directly on the reconfigurable fabric of our FPGA NIC to do exactly that. Obviously, there are some challenges arising from this idea. First of all, DPI must have a high speed to achieve line rate so that we don't lose any of the performance that we try to get from RDMA. And secondly, we need to have a very accurate DPI model, not to make many false positive decisions so that we block unnecessarily our networking traffic. Yes, this is a good point to dive a little bit deeper into the technical intrinsics of the model that we are, or the network stack that we are building on. We're using the RDMA stack that has always been part of the very well-known Coyote shell that has already also been developed here in our systems group at ETH. And since it speaks RoCE, it was our idea that it must be called RoCE Balboa because it hits very hard, actually. Balboa is a RDMA stack for FPGA, which is proven to be fully RoCE v2 compliant. This means that we can do communication with standard commodity NICs, such as Mellanox cards, in a heterogeneous setup. It implements RDMA read, write, and send, therefore the most important InfiniBand verbs. And it also comes with a software environment which allows you to do programming, RDMA programming with those InfiniBand verbs, which is very similar to the commodity NICs that you might already have in your data center. If we now zoom in a little bit, we see the heart of our networking stack, the packet processing pipeline, here on the right. It basically is fed via 512-bit wide XC stream buses that go to the CMAC and therefore to the networking edge. As you can see here, our network processing packet processing pipeline consists of different stages for the different headers that we find in the packet. They are dismantled step by step. So first of all, the IP header, then the UDP header, and finally the RoCE v2 header. Only at the very end of this pipeline, the decision whether to drop or to keep a packet is made. And so there's obviously some kind of timing budget that we have while the packet is wandering through this packet processing pipeline to come up with our DPI decision whether to actually keep or to drop this packet. This timing budget is used by putting our DPI on a parallel data path right next to the packet processing pipeline. In the beginning of our DPI model, which you can see here on the left, you have a payload extractor, which basically strips away all of the headers and of the checksum at the end of the packet and only keeps the payload. The only thing that we keep from the header is the so-called QPAIR number, which is the unique identifier of an RDMA flow that we later use to join our DPI decision with the packet that is wandering through our packet processing pipeline. Within our DPI model, the payload is then fed into the machine learning model, which makes predictions or decisions, and these decisions are now aggregated. Now you might ask, why do we need multiple decisions? Why do we need an aggregator? Well, you have to know that packets are arriving in different sizes, up to 1 MTU, which is the maximum size that a packet can have in our network. But our bus that we are grabbing the data from has only a width of 64 bytes. This means that we're operating on chunks of 64 bytes of 512-bit width. This again means that we need to make decisions in our DPI model for every single chunk of 512-bit width. And only at the end, we can aggregate all these decisions of the different chunks that we have for a single packet. It's basically a time-delayed AND gate that we have there to make one aggregated decision. And this aggregated decision is then forwarded back into the networking packet processing pipeline, where the final drop or acceptance decision is made. We've already talked a little bit about the timing. As you can see, the yellow path is the path that the packet has to take through the packet processing pipeline. This is our timing budget. And then on the other hand, the blue path is the path that our decision has to take. The latency of the deep packet inspection decision depends on different factors. First of all, we've got obviously the execution latency of our machine learning model, which we have here as LML. Then we've got the latency of the overhead that we have in our pipeline, for example, for the payload extractor. And then finally, the most important part is the actual execution time of the machine learning model, which is determined by the MTU of the packet, so the maximum size of the packet, divided by 64, which gives us the maximum number of chunks that we might see for one decision about one packet. The plot that you see here is basically visualization of the impact of both the initiation interval, this factor II, which tells you how long it takes before we can accept the next chunk. In the ideal case, we have an initiation interval of 1, which means that every single clock cycle we can accept one chunk of 512 bits to make a decision about. And the other factor that plays a role in this graphic down here is the MTU. As you can see, the most important factor when we try to get line rate is the initiation interval. We need a model which can accept one chunk of payload at every single clock cycle, more or less, to be able to keep track or to keep pace with our networking stack. Now, to understand how all of this works and how we were able to build a machine learning model which fits these requirements of accuracy and speed, I'd like to hand over to Benjamin, who was mostly in charge of the machine learning part and can tell you more about this.
Thank you very much, Max. So like any good project these days, of course, we do need to have machine learning. Otherwise, I guess probably half the people here would not even be listening to us, right? So before I can talk to you about how we actually trained and deployed these models on FPGAs, I do need to talk about some of the key challenges that we had when actually training these models, right, and deploying them. The first one is a relatively high operating frequency, right? We're still in the FPGA domain, right? We're not building ASICs, and we do have to clock our designs at 250 megahertz, including the networking stack, right? So all of the accompanying components in order to achieve our 100 gigabits per second throughput. Now, again, depending who you talk to, yes, there are people who are going to tell you, yeah, you can get 700 megahertz out of an FPGA, sure, but this is still reasonably high for most FPGAs, right? Second, as Max said, the most important thing really is the initiation interval. Our models have to be able to accept one new input each clock cycle because our networking stack actually accepts inputs each clock cycle. If we can't accept any input clock cycles, that means we provide back pressure to the network. That's already quite bad. But that also then means we have to buffer inputs for future processing. This, of course, then means we have to use block RAM or off-chip memory. And of course, that comes with congestion, closure, right? Timing closure is not easy then. And so it's all just additional resources we don't want. And third, and most importantly, we do want reconfigurability at the end of the day, right? Data center hardware is always evolving. We're getting new workloads, new applications, software is changing. We don't want to write something in Verilog and VHDL that's going to take us like 2 weeks to write, and then it takes us 2 weeks to update, right? This is just not an option. So we want something that we can quickly swap in and swap out, train a new model, update the weights, maybe accommodate for new threats, and then just simply swap it out in a matter of hours, right? Get a new bit stream. So with that, I'll just give a very short primer on HLS4ML. For those of you who are from AMD here, you're already quite familiar with a project called FIN, which is a very closely related project. There has been a lot of close collaborations over years between the two projects. But at a very high level, it's just a framework for taking neural networks from a high-level model, right, Python, down to FPGA IP cores, primarily targeting, again, real-time applications. This was originally born at CERN for ultra-low latency processing there at the Large Hadron Collider, where they produced copious amounts of data when generating these experiments. We're using it in network intrusion detection, where we essentially have still very strict latency constraints and high throughput. So some of the key features of HLS4ML is that it's very flexible, right? It supports a wide range of frontends. It supports QKeras, PyTorch, quantized ONNX, and it's also very easy to use. It supports a wide range of also backends, right? It supports Vivado HLS, Vitis HLS, Catapult HLS, and it's very easy to use from Python. We can tune the performance quite easily and generate new models just out of the box in a few lines of Python code. So To achieve reconfiguration, we've used HLS-FORMEL. To achieve our low initiation interval, we have unrolled all the multiplications, right? So in a neural network, on an FPGA, it's typically implemented in a data flow fashion, which means each layer gets its own set of hardware. And to really accept inputs every clock cycle, we want to do all of the layers in one clock cycle. So we want to use as much as multiplications as possible in one clock cycle. Unfortunately, this does come at the expense of resources, and we do use a lot of DSPs, right? And even modern FPGAs have 10 to 12,000 of DSPs, and if we were to unroll all the multiplications and use DSPs, it would simply not be feasible. We have to use lookup tables on an FPGA to perform our multiplications. Otherwise, we're simply running out of resources very, very quickly. And so what we do is we train quantized neural networks. This has been quite heavily done on FPGAs already. Binary ternary neural networks are very well understood. And then another thing we did for this work is also symbolic regression. It's a generalization of linear regression, which aims to fit an analytical equation to your training data and labels. It can also include cosines, sines, exponentials, hyperbolic functions, and it's the idea is that it could potentially be cheaper than a neural network, right? So we wanted to see how both of these work and to able to fit within the resource budget and the throughput requirements we have. So we have our model, we have our networks, we have our networking stack. Now we want to know how we can actually train this, right? And the main problem with us, with the work we had, is that we actually don't have a data set. There's been a lot of data sets on network traffic, on packets, on aggregated headers, but we're not looking into that, right? We're performing deep packet inspection, as Max said. We're actually looking at the raw payloads you might be sending over the network, such as images, PDFs, files, something like that. And so we don't have data sets, but we have data available everywhere, right? We live in the golden age of internet, which means we can simply go and download a bunch of things. So for executable files, we simply went onto GitHub and IEEE, found a couple of data sets, and we compiled these using GCC and G++. And what we then did is we have a binary file, and we imagine we're sending it over the network. So we simply serialize it into network chunks of 512 bits, right? So we just try to then have as many network packets as that file would have over the network. Similarly, for other files, there's a huge range of data sets online, some from the American government on CSV, docx, SQL files, and so on. And then, of course, for images, there's plenty of files from machine learning and computer vision workloads, from ImageNet, from SVHN, from MNIST, and so on. And again, the idea is we download these files, we chunk them into 512-bit chunks, that's our network bit width, and then we simply do analysis on these individual chunks. So we train these models. We trained 4 types of models. We trained symbolic regression, binary, ternary, and 8-bit quantized models. And we trained each architecture 10 times. So we trained a total of 40 times for 30 epochs. And why we did this is really to be able to get some statistical significance, right? We don't want to train once because we got a lucky hand and say, okay, look, our models are good. No, we train 10 times, and each time we randomly sample files we want to train on. And in total, we trained on 400,000 data points, 20% of which were used for testing. So half and half from files and half from executables that might be used for code injection in your system. We also did a slightly more advanced experiment we like to call code embedding. So rather than just training on 512-bit chunks from files, we also tried embedding smaller chunks, maybe 64 bits, maybe 256 bits, into PDF files, into images, into CSVs, to have a more elaborate attack vector, right? So not necessarily sending an entire executable, but maybe only sending something that corresponds to a few CPU instructions at a time. And this is really more subtle. You could maybe embed a hyperlink in a PDF document that doesn't necessarily take the full 512 bits. Okay, so how did we perform? Well, it turns out we performed quite well because we managed to convince people at AMD to give us the first prize at the AMD Open Hardware Competition. But really, the ternary and the 8-bit quantized model performed very, very well. The binary, not so much. So it has a reasonably lower accuracy. But the ternary and 8-bit quantized model have close to 100% accuracy. And the symbolic regression is a bit lower, but we'll see it saves quite a bit of resources. And then with code embedding, it's quite expected. We do lose a bit of accuracy, right? We lose about 9 to 10% of accuracy, but this is expected because we're operating at a much finer granularity, right? We're only detecting a few bits at a time now, which is, of course, a very elaborate attack scheme, so we do expect to lose some accuracy. The binary model now fell completely off the cliff here, but the symbolic regression is again somewhere in between. But this is really important because that means we can accommodate FPGA systems with different configurations, right? The fact that we use 512 bits doesn't mean that a different system uses 512 bits. They might be using 256 or 128 or something bigger. And that's exactly what's good about our design. It's reconfigurable, but it also can work in principle on other bit widths. And so as a more real world use case, well, we wanted to see what happens if we take whole files now, right? We're not doing our test set anymore. We take whole files that we haven't trained on, and we see how many packets, network packets in a file do I classify as executable or not. And as we can see for the executable one, and for that, we actually went to a third source and compiled again from GitHub from scratch, something we've never seen during training, and we get about 95% packets classified as executable. And then for all the other ones that are non-executable, we want this number to be as low as possible. We want it to be essentially a small false positive rate. The ternary model, again, behaves much better, generally being less than 10%. And then the other symbolic regression has a few anomalies, right? For quite complex files, it goes up to as high as 30%. But what's really important here is if you look at the last three bars, these file types, log, PNG, and SWF, are file types we've never even seen during training. These are file types that have not even been considered during training, which means our models are learning something very specific to executables that is able to diminish them from other file types. And now I just want to very quickly talk about the hardware valuation, right? And what kind of resource footprint we're looking at and latency. Importantly, we did manage to get 1 clock cycle initiation interval. That was the key design goal we had. But also our latency is quite low. Both models perform in less than 50 nanoseconds. The symbolic regression is a bit faster, that's expected. And again, both models are having a very, very small area footprint. The symbolic regression is less than 0.1% across the board, but it does come with some accuracy loss. So my proposal here, and in our experience, is to generally go maybe with the ternary model, and if that is not satisfactory accuracy, potentially use an ensemble of models. So rather than using one model, potentially put 5 of these models. It would still be less than 10% of resources across the board, but you would get more sort of confidence in the prediction. And really, this is after place and route with closing timing. So this is not from an HLS estimate. This is a full place and route analysis. And if we do the network performance evaluation, we can also see that we do batch throughput tests and then ping pong latency style messages over 1,000 iterations on the AMD HACC Heer at ETH. Well, we can see there's basically no difference. There are a few small differences here and there within 5%. These do ultimately come down to the network traffic on the HACC and the ETH network. These are not public, these are not isolated clusters, and they are still part of the bigger ETH infrastructure when it comes to switches and so on. We had a live demo here. I think we will skip this for now in the interest of time. It's a recorded video of about 2 minutes. We can potentially circle back if there's some interest later to this. So in general, to conclude, our contributions are really the first ones that have looked into machine learning-based deep packet inspection for RDMA. And the reason this is important is because, first of all, RDMA is more security vulnerable compared to TCP and UDP, or it can use some of the OS techniques, and it is also more performance critical, right, compared to TCP and UDP. In general, we've achieved 100 gigabits per second throughput, so we're not making any changes to the network, and we're using very little of these resources. And what we've shown so far is that we are in principle able to generalize to completely previously unseen data types and also to much finer granularity than our network bus width of 512 bits. We also have some new work that also tries to test this on malware and other data types, and it is looking quite good. We are trying to extend this to potentially bigger models, but really what this work is trying to say is there's a very clear advantage to using FPGA NICs, since this would really be hard to do on an ASIC-based NIC. Because the network data pad is hardened. And off data pad DPUs would certainly incur data movement costs. On data pad DPUs such as Bluefield are still something that we're considering and trying to see how it would perform against our design. And as some of the future work and work that we're already doing in the group is, of course, we want to extend this beyond DPI. We want to put on compression and encryption there as the obvious choices, but also more complex things. For example, we already have worked with AMD together on putting collectives onto FPGAs. We have quite a bit of work on potentially pre-processing on FPGA for machine learning workloads, but really we want to establish the FPGA as a sort of a device that sits in front of the network and all the other devices and is capable of doing many, many different things. And if you are interested in any of this, please feel free to reach out to us or check out any of our GitHub Coyote is of course open sourced. Our work with AMD on ACL the collectives is open source. This particular project, the DPI, is linked on these slides. And we would like to thank AMD again for the heterogeneous cluster that we conducted these experiments on. And I think we can open up for questions now.